Hello guys, hope so all of you are doing great. Today we'll be looking at a very great algorithm, that is logistic regression, why it is used in place of linear regression during binary classifications or classification problems, and I'll be telling you why we cannot use linear regression for a classification problem in this video. Okay, so do like and subscribe the channel, okay, if you like my content, and let's start. Okay, first of all, why logistic regression and why not we are using linear regression when we have a binary classification problem? Okay, let me just write it down. Linear regression. Okay, why we are not using linear regression, right? All of you might be thinking why, right? Okay, let me just erase this thing here first. Alright, so see how linear regression works. If you remember my previous video, okay, what was the equation for linear regression? What was the value of hypothesis, right? The value for hypothesis is nothing but h theta of x is theta 0 plus theta 1 x1, right? This was the hypothesis, right? And the equation or the line that we get is somewhat in this manner, right? We get a best fit line using this hypothesis. Now, number one thing, let's say we have a classification problem. Okay, we have a binary classification problem, and the problem is something like this. Okay, let's say we have a binary, okay, we have a binary classification problem where we have two params or two output features basically, which is, let's say, in this manner, pass, okay, fail, or you can say 1 0. Okay, you can actually write it in this manner also. So whatever you like, pass, fail, 1 or 0. Okay, and the feature 1 is, let's say, it is some working hours or maybe study hours. Okay, let's say 6 7. Okay, not 7, let's say 2. Obviously, if someone studies only for 2 hours, he may not get that good result, so he can get failed. So 2 hours or maybe 8 hours, 4 hours, so something like this. Okay, let's say this is our feature. Okay, now how can we actually represent all this in this graph? What we can do is we can just say that this is our 1, this is our 0, right? And once we start to plot these points here, how they will be getting pointed? Let's say we have 1, so 1 will be somewhere here, 0th point will be somewhere here, right, in the line itself. So this is how they are going to be plotted, right, in somewhat this manner. Okay, now, but how would we are going to classify this? So what we can do is we can actually create, let's say, a 0.5 here, right? We can write down it as 0.5. Now remember this, I am talking about linear regression for now. Okay, let's say this is 0.5 here. Okay, and we got a best fit line from somewhere here around. Let's say we have a best fit line from this way, in this way, passing from this point. Okay, I'm just taking, this is a random situation. Okay, the real solution will not look like this, but assume this is the, let's say this is how it is going to work for now. Okay, and let's say this is our line, and we can clearly see whatever points we get above 0.5. Let's say we got a point, let's say we got answer as 0.7. So what we can conclude is that it will be 1. Okay, and if we get an answer below 0.5, we can conclude it is a 0, right? So I can simply write here anything above, right, anything above 0.5 will be 1, right, and below, lower than 0.5 will be 0. But suppose just consider this. Let's say we have an outlier. Okay, we have an outlier here, and that outlier actually resulted in placing a value somewhat here. Okay, let's say we have, and there can be multiple outliers, right? And then we got a best fit line like this, right? Now obviously, now solving this question will not work, right? My best fit line changed, right? Now because of this thing here, because of this outliers, we cannot use linear regression for a classification problem. Okay, so because of outliers, well, there are one more thing that in linear regression sometimes you can also get a negative value, right? You can also get a negative 0.1, or maybe you can get higher than one value, which is 2, but this can be solved, but we cannot do this outlier thing. Okay, if we get an outlier, our best fit line will get changed and this will not work properly. So instead of doing that, we use logistic regression. Okay, so this is why we use logistic regression. Now, how logistic regression works and how it actually solves all these problems. Okay, how logistic regression works. Okay, how logistic regression works. Now suppose again we have a binary classification. Let's say we have this thing here. Let's say work hours. Okay, work hours, and then we have an output feature. Okay, let's say work hours are 4, 2, 0, 1, 3. Again there is pass, there is fail, right? There is fail, and somewhat like this type of classification. Okay, now in logistic regression what we use is we use sigmoid. Okay, we use sigmoid function, and that is why logistic regression is a very important algorithm to learn, because see, in deep learning also we use similar things. We use logistic, we use linear regression as an our basics of deep learning. Okay, so let me just show you how it works. So what is a sigmoid? Sigmoid is nothing but this is the sigmoid function. Okay, and what we do is we know that our hypothesis for linear regression is what? It is theta 0 plus theta 1 x1, right? Right? This is our hypothesis. Now what we are going to do is we are just going to wrap this sigmoid function. Okay, why we are wrapping this? Because as you know, in above also we were able to see that to create this thing here, to create, if suppose we get 0.7 as our value, now we want it to be 1, right? So to do all this, we wrap this sigmoid function. Okay, there is one term also you can say. So to squash this basically, so to squash all these things, what we are going to do is we are going to wrap it with a sigmoid function. Okay, in this manner. So this will be how it is going to look like after wrapping. Okay, theta 0 plus theta 1 x1 for h theta x. Okay, hope so you are able to understand it properly. Okay, so we have done nothing, we have just wrapped this whole function, and if I am going to like, if you want to see mathematically how it looks like, this will be nothing but as I told you, sigmoid is 1 upon 1 plus e to the power minus x, right? So after wrapping it, what will happen? Our hypothesis will be, so I can just write it down here. Hypothesis of logistic regression is equals to nothing but 1 upon 1 plus e to the power minus, okay, theta 0 plus theta 1 x1. Okay, got it? Pretty simple, right? So this is how the hypothesis actually look for our logistic regression. What was the hypothesis for linear regression? H theta is equals to theta 0 plus theta 1 x1. And what is the hypothesis for logistic regression? It is this. Okay. But now again the problem is, if we are going to see, and let's say we have a cost function. So if you remember, what was the cost function for linear regression? The cost function for linear regression, okay, this is for linear regression. Okay, this is for linear regression. Okay, what was the cost function for linear regression? If you remember from my previous video, it was 1 by 2m, where m is nothing but number of basically number of points. Okay, so 1 by 2m, okay, sum of all, okay, I is equals to 1 and what was here? R h theta of x I minus y I whole square, right? If you don't know how this cost function comes and how it is actually used, you can just basically check my previous video. I'll share the link in the description itself. Okay, now this was the cost function for linear regression, right? But the question is, what will be the cost function that we can use for logistic regression? Can we use this cost function? Yes, we can, but the thing that will change here is this thing here. Now in linear we have h theta of x as this, right? In logistic regression we have h theta of x as 1 plus e to the power minus theta 0 plus theta 1 x1. Okay, now how we can write it down? We can write it down simply in this manner, right? Now the problem here is that when we are using this cost function, as you can, if you remember, the graph for the gradient descent for linear regression was in this manner, right? This is how it used to come after applying the convergence theorem, right? We actually reach a global minima here, right? This is our global minima and this is what we used to get, right? This was the graph, if you remember it, right? But the problem here is, after applying this formula or this cost function, okay, in respect to this logistic regression equation, right, the hypothesis, what graph we get for logistic regression, let me just draw it in next area. Okay, all right, for logistic regression, our graph comes in this manner. Okay, when we are using sigmoid activation, okay, when we are using sigmoid activation, our graph comes in this manner. It is something like a zigzag. Okay, if I can just draw it properly here for you. Okay, now, clearly this is not that proper, but just consider it. Okay, something like this. So okay, right, now what is this value here? This is nothing but 0, and what we call it? We call it as our local minima. Okay, we call it as our local minima, and this is our global minima. Got it? But the problem here is, how we will be able to understand if we are getting so many local minimas, right? We need to actually make it simplify. We need to simplify this, right? So to simplify this, what we do is, to make this curve simple, okay, I'll just write it here. To make this curve simpler, what we are going to do is, we are going to change our cost function a bit. Okay, and what formula we do use? We use a simple formula which is nothing but this. So whenever okay, whenever, okay, understand this, okay, whenever our y is equals to 1, okay, whenever our y is equals to 1, okay, and whenever our y is equal to 0, we are going to use log of h theta x, okay. What we are going to use? We are going to use log of h theta x, okay. And whenever our basically our y is equals to 0, what we are going to use? We are going to use minus log, okay, here is also a minus, okay, minus log 1 minus h theta of x. I'm trying to write it down properly, sorry for the bad handwriting, okay, got it. This is how we are actually going to use our cost function, okay. This is what we do to actually make it a simpler trajectory, to basically create this trajectory a simpler trajectory, okay. After applying this thing here, now our graph will be like in this manner, and convergence theorem remains the same as I showed you in the linear regression, okay. See guys, if you have not yet seen the linear regression video, this video will be a bit tougher for you to understand, but if you have seen the linear regression video, this will be a bit easier for you to understand, okay. Now, why this? How this graph comes, again if you are having a doubt why this graph will come like this way after applying this, so let me just show you here also. What will happen here is now that after applying this cost function, what our graph will look like, okay. Let's say we have y is equals to 1 here. I cannot just prove it in front of you because it will take time, but I'll just show you how the graph will look like if you apply this. It will look like in this manner, okay. So log h theta of x, okay, alright. If I am plotting a graph, okay, if I am plotting a graph between log h theta of x and h theta of x, okay, how this will come? This will come in this manner, okay, in this manner, in the downward trajectory, okay. And for y is equals to 0, our graph will be in this manner, okay, the upward trajectory, alright. And that is how we are actually going to do it. So after summation, or I'll say after actually applying these values into our equation of cost function, our cost function will look like somewhat in this way, okay. So what will our cost function look like now? 1 by 2m sum of all, okay, m I is equals to 1, alright. Now y of I, okay, log h theta of x, sorry for this bracket here, log h theta of x, okay, I, and addition 1 minus yi, alright, log of 1 minus h theta x, alright. So that is how we are going to represent it. This is how it is going to look like, okay. Now, and what will the convergence theorem that we are going to use? That is again the same thing. Theta j is equals to theta j minus derivative of learning rate j, and alpha is our learning rate that I forgot to multiply, theta j. And what is j here? J is nothing but the cost function, so let me just write it down. Theta 0 comma theta 1 and theta 0 comma theta 1. Fine. So this is our equation for the convergence theorem. This is our convergence theorem here. Alright. This is our, let me just write it down again, convergence theorem. Okay, this is our convergence theorem. So hope so you guys were able to understand how logistic regression works. Okay, and again, one more thing that I forgot to actually explain. Yeah, I forgot to explain the graph of sigmoid. Okay, really sorry about that. So sigmoid is represented in this way. Okay, so how our graph actually comes after applying a sigmoid function. Okay, the actual point graphs. Okay, the graph that is actually going to tell you. So the graph of sigmoid after applying sigmoid activation is this. Okay, so 0.5, 1 and 0, and then we will get something in this manner. Okay, alright, this is how we are going to actually get a graph. It would be a more streamlined, but it's fine for now. Okay, that is how it is going to look like. So this was all for logistic regression. Okay, logistic regression is a very great algorithm. Okay, this was the whole math intuition behind logistic regression, and hope so you were able to actually understand. And if you still are having any doubts, you can just comment it down in the comment section and I'll explain you. I'll try to do my best. Okay, and yep, thank you for joining in. Hope so you all were able to understand it, and have a good day. Keep learning, keep enjoying. Bye bye.